Siggraph course page. And there's some good presentations here. The background one is the one we're going to do today, but over the next few days, we'll go into some of the other game-specific implementations, like what choices did Call of Duty Black Ops 2 make, and what choices did Unreal Engine 4 make. Like these are all nicely. They've been very open about the lighting models that they use. And, we're going to take advantage of that to get a huge head start. But today is going to be this presentation. What I want you to note is that at Siggraph, this presentation took 15 minutes. And I don't think it's going to take us 15 minutes. This one took 20 minutes, this one took 20 minutes. I expect each of these to take like an hour because of how in-depth they are. I don't know how they can get through it in 15 minutes.
Wait, just right now, theme song. It makes it more dramatic. Can you physically they shake?
To an hour minutes. Natty presents the underlying shading and the math to describe different physically based rendering techniques. So here's an example of what happens when light interacts with matter. And the model that everybody uses is you have the surface layer where the light comes into contact, and then you have some of it reflecting off of the surface. That part is the part we call specular. And then you have another portion of it, the remainder of those light rays going into the surface, bouncing around all of these particles that are inside this matter, and re-emerging, scattering in some other direction in practically random directions, and that portion we call diffuse. So he's going to break down each one individually. He's going to start with a single light ray, and when light passes through a homogeneous medium where there's no barriers to any kind of surfaces, it just travels in a straight line. It's pretty simple. Some homogeneous media don't significantly change the color of that light ray, like this clear glass of water. Whereas others absorb part of the light that's passing through it. So like this liquid right here absorbs the blue, which is why it looks red. And he nicely shows, like, you have a color, the color of the light starting off, and then the more it passes through the medium, the more that medium absorbs more and more of that medium's color, right? And so you get less and less blue and more saturated red. Scale is very important. So everybody knows that a glass of water looks like it doesn't absorb any of the incoming light. It pretty much just lets the light pass through, without modifying the color or the intensity. But you take that same water and you put it in a pool or you put it in an ocean, and now all of a sudden you can tell that it actually is absorbing a little bit, like every inch or so of that water absorbs a really tiny amount. Over long ranges, the color change is quite dramatic. So water absorbs like red, and so you're left with like a blue or a cyan. In an inhomogeneous medium, then the property that is important to the physics is called the index of refraction. And that causes light to bounce around in different directions. So it alters the direction of that light. And that term is called scattering. So in this example, you have the light coming in, and then depending on the properties of what's inside that ball, it will scatter the light and send it in a bunch of different directions. So here's a cloudy liquid, and it's cloudy because it's an inhomogeneous medium where you have some different size particles suspended in the water. And as the light bounces off each one of these particles, it changes the direction and causes this big light ray, which is many photons. And it causes some of them to scatter and go in all different directions. And depending on how dense that liquid is, or how the particles are laid out, it's going to scatter more or less. So this is a cloudy medium, and it's dense enough to randomize the light's direction somewhat, but not completely random, right? Because you can still sort of see through it more or less, but it just kind of like spreads it a little bit. Whereas if you take a glass of milk, like milk is recognizable because it completely scatters any light that comes into it. It doesn't absorb very much. So this is low absorption but high scattering property. And you know, it's very recognizable as milk. Milk, for the most part, appears opaque. Like you wouldn't really consider milk opaque, but if the light isn't really, you know, getting to the other side, then that's kind of the definition of opaque. So scale also matters for the amount of scattering that happens. Air, everybody recognizes as it doesn't scatter very much. But then if you look on the horizon, over the course of miles and miles, then all of a sudden scattering becomes obvious. And you look up into the sky, the reason why the sky is blue is because it scatters the red more than it scatters the green or the blue wavelengths. So scattering is definitely scale dependent, just like absorption is scale dependent. So the three different light properties that Maddie breaks down in 3 categories are light can be absorbed by whatever matter it's passing through. Light can be scattered off of whatever matter it's passing through, and light can be emitted, like in the case of any of these light sources. And for the purposes of physically based rendering, we mostly care about the surface of the light interacting with a surface. And so he doesn't discuss the emission part. So he's just going to focus on the first 2. Here's a nice little chart that shows, you know, the different axes. Like, if you go to the right, each of these liquids is increasing its scattering. It doesn't absorb very much. See, like this is at the bottom, no absorption. So none of these, or these different liquids have very little absorption, and that gives them like the white appearance. But as you go to the right, it scatters the light, you know, increasing amount. And you can definitely see the difference. Up here, we have absorption. As you go up this, like these are each absorbing different wavelengths. As you go to the right, you can see that they're also changing in cloudiness because it's increasing in scattering. And then you have like this dark liquid up on top, which is dark because it's absorbing most of the incoming light. And it's, you know, in this column because it scatters, you know, it spreads the incoming light at a medium scattering. These are the types of materials that we care about. These are the ones that we are trying to simulate with our whatever shading solution that we choose. So you may recall that a few slides ago, abrupt changes in index of refraction constitute scattering. Small particles like those found in cloudy liquids are one special case. They scatter light in all directions. Another special case is what happens when light hits a surface. And at that surface barrier, you have one type of matter, like air, and then another type of matter, like concrete or glass or something. Like each type of matter has an index of refraction. And everybody's seen this type of chart before where the reflected angle, right, if the light is coming in from this direction, then the reflection angle is exactly the same as the incoming angle. But the refraction angle changes based on the index of refraction. All of the common models use a representation of the underlying geometry called microgeometry. So you can't actually see it. It's at a scale that's smaller than like a pixel on a screen, but you can definitely see the effects of it. And so roughness, for example, like how rough a surface is, you can't always see how rough the surface is. You can't see the geometry being any rougher, but you can definitely see you can tell that the microgeometry is different. And he has this really nice example here where on first appearances, like if you just look at the shape of this and the shape of this, like both of these bowls, I think these are just bowls that he turned upside down, both of these bowls look to be about the same shape and about the same smoothness. Like if you were to touch these, they would probably feel very similar. They'd feel very smooth. But take a close look at the specular reflection, and you can tell that this one is much more blurry than this one. And the only difference between this is not the macro geometry, but the microgeometry. So he sketches, you know, maybe the microgeometry is like little ridges on this one, and so it pretty much preserves the scene around it. But then this one is much rougher, and so it becomes a blurrier scene. Multiple directions. So each one of these incoming light rays bounces off one of those little micro mirrors. But since we can't see them individually, the overall shape of it makes it look like a single light ray is coming in and then many are coming out. But it's actually like each light ray or each photon is coming in and bouncing off of whatever shape that it's bouncing off of. It's just the scale matters. So what happens to reflection is pretty easy. It's pretty easy to understand. What happens to the light that doesn't get reflected immediately but goes into the medium? And for metals, it just gets absorbed. So metals are entirely specular. They don't have any like diffuse component. So for non-metals though, and he'll go into those two categories in more detail. For non-metals, you have the remainder, so you have a portion of the light bouncing off of the surface, and then the remainder of it going into the surface, and depending on the properties of these little particles in here, it's going to bounce around and then come back out. And for simplicity, most of the time, what goes in and comes back out, which we'll call the diffuse term, that's actually subsurface scattering. So diffuse is always subsurface scattering, but for the most part, if it bounces around and then leaves the surface close to where it entered, then we don't need to get any like fancy subsurface scattering formulas in there, right? And most surfaces have this kind of behavior where the distance between the entry point and the exit is close enough or small enough, like it's less than a pixel on the screen, for example, then you can just assume, or you can treat that as if it was coming in and leaving at exactly the same point. And that just simplifies the equation. You know, I'm sure you guys know that subsurface scattering is kind of hard to simulate. So this is, for example, this square region right here is like a pixel. And then the light is coming in here, and it's leaving here, and it's leaving here. And as long as like the general vicinity of where it's leaving is close to where it entered, we can ignore the fact that it's subsurface scattering. And we can just say like, well, a certain percentage of the incoming light just left at the same exact point. And so that's just all those same arrows. Instead of them being like kind of randomly distributed spatially, they're all leaving exactly the same point. Like we've been saying, the part that reflects off of the surface is the specular term. The part that is subsurface scattered and then comes off is the diffuse term. This is just saying that if the amount of scattering under the surface is large, in the case that you're zoomed into the surface, or it's like wax, or it's like skin, right? Then subsurface scattering does become an important part of that equation. But that's harder to simulate. And even like skin, which we know is like very translucent and has lots of subsurface scattering, can be modeled as completely diffuse local scattering if you're far enough away. Because at that point, the scale, like the size of the pixel, is kind of covering the area that the light kind of entered and exited. So this is the part that you guys came for, right? It's the math, right? The term that all of these formulas use is radiance, the measurement of like how bright the light is coming in at a certain angle, which measures the intensity along a single ray direction, and it's a spectral, so it's a color value. So obviously you can have orange light or red light or green light, and so the color of the light matters, and all of these properties are spectral, which means that they cover the entire spectrum of wavelengths, not just the red, green, and blue. But for the most part, we simplify everything by just saying how much red, how much green, how much blue is in this lighting term. And we just worry about those components individually. And that just really simplifies things. And for most things, that's a fair simplification. Okay, so light can be handled locally for most surfaces, which brings us to the heart of any physically based rendering equation, which is the BRDF, the bidirectional reflectance distribution function. And it looks messy, but basically it's a function. It's really like a percentage. So for a given surface, all we really care about is what percentage of light that came in at a certain angle gets reflected at a certain angle. And that's all this function represents. So it's the percentage of light that came in from some direction L, like that, and is leaving in some direction V, presumably because that's where the camera is. It's called V because it's usually the view direction. So like light comes in and bounces in many directions, but if there's nothing there to see it, right? If there's no camera, then you don't really care. So this formula gives you, this tells you how the surface handles a given light direction and reflects it in a given view direction. And the way we plug that in to get the light that's coming out is the integral, which, if you've taken calculus, everybody's taking calculus, right?
A long time ago, and very poorly.
So it's not a big deal. Like this looks scary, but even the experts don't necessarily solve this. They start with this, but then they'll open up MathCAD or like MATLAB and just plug their formula in and let MATLAB solve the integral for them. So it's not like anybody's like solving integrals actively. But what this means conceptually is that the light that's being emitted in, let's say, the camera direction, so if you're looking at a surface, the light that's coming out towards you is equal to the sum over the hemisphere of that surface, and the hemisphere meaning, based on the surface normal, the hemisphere above that, because you can't have, if it's an opaque surface, the only light you're going to see is the stuff that comes back out on the hemisphere. And so it's equal to the sum of all of the incoming light, which is L sub I, right? This one's L sub O, outgoing light. The incoming light in every direction L, multiplied by N dot L, which is it's like a weighted sum. If light is coming in straight on the surface, you're going to get a brighter contribution than light that was coming in at a glancing angle to that surface. And that's what this N dot L term gets you. Multiplied by, and this is just a component-wise multiply, meaning you multiply the red, you multiply the green, you multiply the blue independently. Multiplied by the BRDF, right? Because this is like what percentage, this is like a percentage. What percentage of light that came in from a given angle gets reflected in the camera's direction. And so you have to add up all of the incoming light that came from all angles and what percentage of that is being reflected back towards the point that you care about, like the camera. So the specular term is the first thing he's going to break down. And the theory is that the microgeometry, which you remember from the other slide, is perfect mirrors. So if you go down to a scale small enough, you can treat the underlying geometry of the object as a bunch of oriented mirrors. And so if you have like the sun rays coming in, for example, all parallel, then depending on which point they hit, they're going to bounce off in a mirror direction based off of these little micronormals. And so you get some of them going this way, some of them going that way, and so that's the spread that you get. And the important thing, right, so when I said micronormal, that's because it varies. It's not the same as the surface normal. There's only one surface normal for your low poly mesh. But the normal that will reflect light off of a mirror in a given direction, right? If the light is coming from this direction and we were viewing from this direction, there's only one angle, there's only one normal. And it's the normal that's halfway between the direction and the view direction. That's the only orientation that's going to reflect light off of a mirror back in towards the viewer. And so the angle, the normal that we care about is called the half vector. And so any type of, the percentage of micronormals that align with the half vector, those are the only ones that are going to send light back towards the camera. Another term is shadowing, which we know that from the macro scale, right? That's when an object blocks light from hitting a surface. And so there's going to be some microgeometry that is not receiving light, even though the macrogeometry is. And that's called shadowing. You can see that the ray hits another piece of microgeometry, and it stops, it doesn't reach that part of it. And then there's masking, which is the analog or the mirror of that, where some of the microgeometry surface is just not visible to the camera. And so it's kind of like the mirror side of shadowing. Shadowing and masking are very similar, but looking at it from two different directions. Multiple bounces. Most of the current BRDFs just ignore multiple bounces, right? Because of course, if the light stopped here, it would bounce and hit another portion and maybe bounce a few more times and come out. That's really complicated. And so none of the current models, maybe there'll be future models that handle that, but all of the current ones just assume that any light that is either shadowed because it hit another portion of the surface and then didn't hit another portion, or masked from the camera, is just gone, it's just lost. Just for simplification. And this formula isn't that bad. It looks bad, but we're just going to spend a minute on it because every one of the formulas you're going to see on the Call of Duty or the Unreal Engine or 1886, like all of them are going to start from this formula, and they're going to substitute in different terms for each of those different letters there. So to wrap it up, this one is our BRDF, and it says that we can represent the BRDF, meaning the percentage that light comes off of a surface in a given direction, as the multiple, or multiplying these different terms, these different components together. And there's a Fresnel component. Everybody's heard of the Fresnel effect. And then he'll show a slide that goes into more detail on that. Then there's the geometry component, like the shadowing and masking terms, like how much does the roughness block light from hitting the microgeometry and how much does it block it from going towards the camera. And then there's the normal distribution. Notice that it passes in the half vector, because that's the only, all we care about is what percentage of micronormals are aligned with that half vector. So this one's the Fresnel reflectance, and the Fresnel reflectance is the fraction of incoming light that is reflected as opposed to going into the surface. And since we're talking about specular, we only care about the percentage that's reflected directly off of the surface. And all of you are very familiar with this. If you take water, for example, If you look straight down on water, which means that you're looking directly aligned with the normal, right? It reflects very little. Like, it's really hard to see your face if you were looking down on water. It's really easy to see somebody else's face if you were looking at a grazing angle to water and somebody else was in the water. You can easily see their face. And that's the Fresnel effect. And pretty much all materials follow these kinds of curves right here. So if we just follow water, you see that water is not very reflective up until about 45 degrees. So you look at water from straight down to 45 degrees, you're mostly seeing through the water. You're not seeing the reflection. You're only seeing like 2% of the sky or whatever. And then around 45 degrees up until 70, you start to get a significant amount where you're getting like 10, 20% of the above, the sky reflecting in the water. And then it skyrockets, right, from 70 to 90. At 90, if you notice, like all those different curves converge to 100% reflectives. So pretty much every object that is solid that we deal with is 100% reflective at 90 degrees, at grazing angles. It doesn't mean that it doesn't scatter, but it just means that none of the light is going into the surface and coming off diffusely. It's all coming off speculatively. Most nonmetals are monochrome specular. So this solid line is the line for water. So it's like 2%, and then it goes up to 100% at grazing angles. Glass starts off at around 4%. So you can see, if you looked at yourself in a glass window, the reflection that you'd see would be about 4% the brightness that somebody looking at you would see. If you took a camera, like if you took a selfie and of yourself and you took a picture of your reflection in the piece of glass, they would be about, what was that, 25 times difference in brightness, because the window would only reflect 4% of you if you look straight at it. You can see perfect mirror reflections in windows if you look at it at an angle, because at 90 degrees it goes up to 100%. Whatever comes in at that angle is reflecting off 100% of that. So it's hard to see yourself, but it's really easy to see somebody that's like at an angle from you. Diamond is one of the highest specular nonmetals, and that's at around 18%. And then that also goes up to 100%. So, that's kind of one of the properties that women like about diamonds. It is noticeably more reflective at all angles. This is the least reflective angle that it could be, and it's pretty reflective. It's almost 20%. And that's why, it sparkles more than a plastic shaped like a diamond. And then we get into the metals. Metals are really high reflectance, really high specular reflectance. Iron is a monochrome specular, so it's like a gray. It starts at above 50%, and then it dips down a little bit, which is kind of weird. But again, it meets up at 100% towards the top. These other two, aluminum, copper, gold, those are colored specular. So metals are really the only things that have colored specular. Non-metals, like all these things down here, are all monochrome specular, and very low at that. And so obviously, like copper has a different curve for the red, green, and the blue. I guess this one would be the red, because copper is mostly red. So you can have colored specular, but really it's meant for metals. Teapot, just showing the Fresnel term by itself. Notice that if you look straight at it, it's pretty much black. You don't really get much reflection. And this image is really just showing, like, what if you were in a white room? Like, what if it was completely overcast and it was just uniformly bright everywhere? Like, how much would you get from the Fresnel term? and you wouldn't really get much when you're looking straight at it. You'd only really get the environment reflecting at grazing angles. Talked about that part where we can simplify. Like, these are complicated formulas, but if you just consider these three regions and what they do, for the most part, from 0 to 45, it stays flat. And then it goes up slightly from 45 to 75, and then it goes up to 100% at 90 degrees. Then we can like come up with simplified formulas for these. This is showing those three different green, yellow, red regions from the graph on the teapot. Microfacet, BRDF. Okay, so I think now he's going to go into like how many of these microsurfaces are oriented. So, the important characteristic, the one that we paint into our textures, is the surface's characteristic specular color, C-spec. What we paint in our textures is this column right here. So it's, for water, we would paint like a 2% black, 2% gray in our specular texture. For plastic, it would be like a 4%, which is around 56 if you were in Photoshop, 56 sRGB. Diamond would be one of the highest non-metal specular textures. And then when you get up into the metals, you would paint the color of the copper. Like what you think of as the color of copper would be your specular color in your specular texture. What's interesting, most people don't realize, but like things like copper, it's reddish. It's like orange, reddish. But at grazing angles, it becomes like a white. It doesn't tint the specular anymore because the Fresnel effect makes them all go to 100%, all three red, green, and blue channels. So this is your specular texture. And he has some example colors for some metals. So basically for metals, specular texture is what you think of as the color of that metal. Metals don't have any diffuse, it would be black, a black diffuse. One side note, when you paint in Photoshop, whenever you use an 8-bit image format like DXT1 or DXT5, you are painting colors in sRGB space, which is standard RGB, standard gamma space. And you would take each of these numbers and multiply that by 255, or you'd grab the percentage slider. So when you're using Photoshop, these are the colors that you would use in your color picker. When you're doing like the physics calculations, the colors that I would use after I get your textures would be this side, which is the same. These are the same colors, but in linear space. And basically, when you paint in your gamma textures, your Photoshop textures, you're not painting linear brightnesses. You're painting a nonlinear brightness because you only have 256 shades to work with. And if you just had 256 actual uniform brightnesses, you get horrible banding. It's not a good distribution. And so for many reasons, but that one's a nice side effect, you paint in a warped, nonlinear space, sRGB. All of the physics needs to happen in linear space. And so we just did this on the Mohawk project yesterday, but we converted the space that the calculations are done from gamma space into linear space in preparation for our switch to physically based rendering. And the good thing is that it's pretty much a free conversion. For the past 10 years, maybe even more, all hardware has been able to convert these colors, sRGB colors, into linear space practically free. It's like built into the hardware because they know that this is something that everybody's going to want to do. Likewise, we present the output to a monitor that only has 256 shades. And so again, it converts this back into the sRGB for good, like for the least banding, for good preservation of color range. And the hardware to convert back from linear to sRGB when you render to the monitor is also built into all hardware. So these conversions are not expensive at all. These are the specular textures that you would paint for non-metals. Water is 0.15 sRGB. And if you multiply that by 256 or 255, you would get like 37. So that's like a 37, you know, if you were just in your color picker, 37, 37, 37, because it's gray. That's a really dark specular. And that's what you would need to paint for water. The reason why we think water is so reflective is the Fresnel effect, where at the grazing angles, it goes from your really low percentage, your 2%, right? 0.02 is 2%. It starts at 2%. That's what you paint. You paint where it starts. But then, depending on the angle, it goes all the way up to 100% reflection. Glass, plastic, is between 0.3 or 3% and 5. And that's like, I think a good ballpark is like 56 in your Photoshop color picker. Rubies, as you get to the gemstones, everybody likes gemstones because of this property. They are the most reflective non-metals. Diamond is up to 17%. So this is a formula that you don't need to worry about. Basically, this is how we take the specular color that you paint, and we ramp it up to 100% at grazing angles. So I'll worry about that for now. So we talked about the Fresnel term, and that's the characteristic. That's like what you paint into your texture. The base specular, the minimum specular, if you were looking straight at the surface, that's what you paint. And then that formula ramps it up to 100%. Next, he talks about the normal distribution function. And that's another thing that you won't need to worry too much about. There's a whole bunch of different options. Everybody chooses a different one. Some of them are blobby, and some of them are, so this is like the shape. This is the shape of the highlight. And like, do you want a sharp peak and like a sharp fall off? Or do you want more of a smooth peak, like a blobby peak with like a longer tail, right? These are just different options and different, and really this property is a factor of what's the shape of the microgeometry. And so this is just a model for describing the shape of the specular height, the hotspot. And so that's the D term. We just breezed through that. The G term was the shadowing and masking term. If you group this section with those two terms down at the bottom, that new term is called the visibility term. And the simplest possible one is if you just assume that that's 100%, meaning that there's nothing, the microgeometry is not shadowing, it's not masking anything, and that everything is kind of like balanced out, which isn't true, but that's what most models use. And so if you put a 1 for all of this stuff, then you can see it really simplifies things. You have that Fresnel term, which is your specular texture going up to white, and then you have the shape of the highlight, and divided by 4. I mean, that's pretty simple. Some more complicated terms.